Your reality is just one thread in an infinite tapestry. We are about to explore 30 mind-blowing theories about quantum timelines and the multiverse. This journey will take you through the strangest corners of theoretical physics, and it will challenge everything you think you know about what is real. By the end, you will possess a new framework for understanding existence itself. We will see how a single decision might spawn a new cosmos and ask if our consciousness creates the past. How solid is the history you remember? Which of these possibilities feels most like truth to you? The idea that reality splits with every choice began not as science fiction, but as a serious mathematical solution. In the 1950s, a young physicist named Hugh Everett III proposed a radical answer to the quantum world's strangest behavior. He called it the many worlds interpretation. It suggests that at the quantum level, every possible outcome of every event actually happens. The universe does not choose one path, it takes them all. Take the famous thought experiment of Schrödinger's cat. In the classic version, a cat in a box is both alive and dead until someone looks, a paradox highlighting the absurdity of quantum rules in our everyday world. But Everett saw it differently. He argued there is no paradox at all. The moment the quantum trigger inside the box is activated, the universe splits. In one new, perfectly real branch, the cat lives. In another, equally real branch, the cat dies. Both outcomes are concrete. The act of opening the box does not determine the cat's fate. It merely reveals which branch of reality you, the observer, are now in. This transforms our understanding of free will and destiny entirely. Every decision you make, from a monumental life choice to whether you turn left or right at a street corner, is not a single act of selection. According to this theory, it is a branching point. In one timeline, you took the job offer and moved across the country. In another, you stayed. Both versions of you are real, living out the consequences of that split second. This means there is no single destiny written in stone. Instead, there is an ever-expanding tree of destinies, a cosmic library containing every story that could possibly be written. Your life is not a single narrative. It is the collection of all its possible variations, each one as valid as the next. But for decades before Everett's radical proposal, a different theory held sway over the quantum conversation. This is the Copenhagen interpretation, the traditional framework that still forms the bedrock of how many physicists understand the quantum world. It offers a starkly different picture of reality. Where many worlds says every possibility becomes real, Copenhagen suggests something far more elusive and strange. It proposes that a quantum particle, like an electron, does not have a definite position or state until we measure it. Instead, it exists in a blurry cloud of all possible states at once, a condition called superposition. Think of a spinning coin while it is still in the air. Is it heads or tails? According to Copenhagen, it is genuinely both, a true mixture of the two possibilities. The act of observation, of looking at the coin, is what forces it to land on one side or the other. This moment is called the collapse of the wave function. The observer, by the very act of measuring, is not just discovering reality, they are creating it. This places human consciousness, or any measuring device that acts as an observer, in a uniquely powerful and puzzling position. The famous physicist Niels Bohr, a champion of this view, once said, "If quantum mechanics hasn't profoundly shocked you, you haven't understood it yet." The shock comes from the implication that there is no objective world sitting out there, fully formed, waiting for us to find it. The universe at its most fundamental level is a realm of pure potential, and it only crystallizes into the solid world we know through our interaction with it. This leads to profound philosophical challenges. What exactly counts as an observation? Does a camera qualify, or does it require a conscious mind? And if reality is not fixed until observed, what was the world like before the first conscious beings evolved? The Copenhagen interpretation gives us a universe that is fundamentally participatory, where we are not just passengers but co-authors of existence, constantly collapsing infinite possibilities into the single, seemingly solid timeline we call now. The clash between many worlds and Copenhagen leaves us with a universe that is either endlessly branching or fundamentally fuzzy until observed. But what if both are missing something? A third, often overlooked theory offers a radically different vision, one where reality is neither split nor uncertain but beautifully, classically solid. This is the de Broglie-Bohm pilot wave theory, a deterministic alternative that dares to restore a single, concrete timeline. In this view, the quantum weirdness we observe is not a feature of reality itself, but a veil hiding a deeper order. The theory proposes that every particle, like an electron, always has a definite position and a definite path. It is never in two places at once. So what creates the famous interference patterns and probabilities of quantum mechanics? The answer lies in a hidden companion, an invisible guiding hand known as the pilot wave. Think of a surfer navigating the ocean. The surfer is the particle with a real, tangible location on the board. The wave beneath them is the pilot wave, a field of influence that spreads out across space, carrying information about the entire environment. The surfer does not control the wave. Instead, the wave's shape and energy dictate exactly where the surfer can go, guiding their path with perfect precision. In the quantum realm, this pilot wave is a mathematical entity that surrounds each particle, interacting with itself and the waves of other particles. It contains all the information about possible paths, but the particle itself only ever takes one. This elegant idea completely sidesteps the need for a mysterious wave function collapse. There is no moment where possibilities suddenly snap into a single reality because the particle was always on one specific journey. The probabilities we calculate in quantum experiments simply reflect our ignorance of the particle's exact starting conditions within the pilot wave, not any inherent randomness in nature. This introduces the concept of hidden variables, aspects of reality that are real and definite but currently beyond our measurement. The pilot wave is such a hidden variable. It orchestrates the dance of particles from behind the scenes, creating the illusion of chance and superposition while governing a perfectly deterministic cosmos. In a de Broglie-Bohm universe, your timeline is singular and unbroken. Every event, from the decay of an atom to the firing of a neuron in your brain, unfolds along a predetermined path set in motion at the dawn of time. This feels comforting, a return to a clockwork universe, but it comes with a profound and strange consequence, something called non-locality. Non-locality is the strange price of this cosmic certainty. In a pilot wave universe, a change to the pilot wave in one location can instantly affect a particle on the other side of the cosmos, a connection that defies the speed of light. This suggests a universe where everything is intimately, instantly connected, a single woven fabric where distance is an illusion. It is a universe of profound order, but also of spooky, instantaneous links across vast emptiness. Yet for all its elegance, this theory of a single, guided timeline remains a minority view, overshadowed by interpretations that embrace the weird. And one of the strangest consequences of the many worlds view pushes the idea of personal survival to a chilling, logical extreme. This is the thought experiment known as quantum immortality. Imagine a device is pointed at you, triggered by the random decay of a single radioactive atom. In any given second, there is a 50% chance the atom decays and the device fires, and a 50% chance it does not. According to the Copenhagen view, you run the experiment once, and you have a coin flip's chance of living or dying. The wave function collapses to one outcome, but in the many worlds interpretation, both outcomes must occur. The universe splits. In one branch, the atom decays, the device fires, and you die. In the other branch, nothing happens and you live. Now, here is the unsettling pivot in perspective. From your subjective point of view, as the conscious observer at the center of the experiment, which branch do you experience? You can only experience the branches where you remain alive and conscious. In the branches where you die, your conscious experience ends. So, no matter how many times you run this so-called quantum suicide experiment from your first-person viewpoint, you will always find yourself in a timeline where the atom did not decay. You will witness a miraculous string of 1 in a billion survivals, each time watching the device fail to fire. To you, it will seem as if you cannot die from this probabilistic event. You have become, in a deeply personal sense, immortal within the multiverse. This is not a suggestion that you become invincible. In countless other branches, your body dies in every conceivable way. But your stream of consciousness, the thread of experience that feels like you, only continues along the paths where it can continue. It hops from timeline to timeline, forever avoiding the termini. The implications are dizzying. It transforms death from a universal endpoint into a personal horizon you never reach. You would not see loved ones age and pass away around you in a single timeline. Instead, you would eventually find yourself in branches of reality where medical science advanced just in time, where accidents were narrowly avoided, where civilization persisted through crises that wiped it out elsewhere. Your personal history would become a narrative of impossible luck and survival, stretching forward indefinitely. This forces us to ask a deeply philosophical question. What is the self in an infinite multiverse? If countless versions of you die every day, but one conscious thread always continues, is that thread truly you, or just one version among an infinity of ghosts? The theory offers no comfort, only a stark logical deduction from the rules of many worlds. It suggests that from the inside, life might feel like a perpetual escape, a never-ending series of narrow misses across an ocean of your own corpses. It is an immortality not of triumph, but of endless branching persistence. And if this is true for you, then it must be true for every conscious being, weaving their own threads of survival through the cosmic tapestry. This leads us to another profound mystery about the nature of observation itself. If consciousness is this selective filter guiding our experience through the multiverse, what role does it truly play in shaping reality? Quantum immortality presents a stark picture of consciousness navigating infinite branches. But what if the multiverse is even vaster and more alien than that? To find a truly cosmic scale of alternate realities, we must look not just at quantum decisions, but at the very birth of our universe. This brings us to the theory of cosmic inflation and a level 2 multiverse, a realm where the laws of physics themselves are up for grabs. The story begins in the first incomprehensibly tiny fraction of a second after the Big Bang. According to the theory of eternal inflation, our entire observable universe is just one bubble in a frothing, endless sea of spacetime. Imagine a pot of water coming to a furious boil. Each rising bubble is a separate universe, nucleating and inflating at fantastic speed, carrying within it its own unique set of physical laws. Our cosmos is one such bubble where the inflation field that drove this hyper-expansion finally settled down, releasing its energy to form the matter and radiation we see today. But crucially, in this eternal picture, the boiling never stops. Outside our bubble, the inflationary field continues to rage, endlessly spawning new bubble universes in an infinite, ever-growing cosmic foam. This is a multiverse of a fundamentally different kind than the quantum branching timelines. Those branches, the many worlds, all share the same fundamental constants, the same speed of light, the same strength of gravity, the same charge of an electron. They are different outcomes from the same underlying rulebook. The bubble universes of eternal inflation, however, can have entirely different rulebooks. When each bubble forms, the inflationary field settles into a random, stable state. This final state dictates the local laws of physics. In one bubble, gravity might be 10 times stronger, making stars burn out in a cosmic blink. In another, the nuclear forces might be too weak for atoms to ever form, leaving a universe of scattered particles. In yet another, the constants might be just right for chemistry, life, and conscious beings to emerge, a bubble like ours. This concept, called the Level 2 multiverse, means that literally every possible configuration of physical laws exists somewhere in the infinite froth. Somewhere there is a universe made entirely of crystal, or where time flows backward, or where space has 7 dimensions. It is a canvas of ultimate possibility. The profound implication is that the fine-tuning we observe in our universe, the seemingly perfect balance of forces that allows for our existence, is not a miracle. In an infinite ensemble of bubbles, a few will, by sheer chance, have the right numbers for complexity. We do not live in a special universe, we simply live in one of the habitable ones, a rare but inevitable oasis in a desert of cosmic dead ends. This connects back to our quantum timelines in a fascinating hierarchy. Within our single, finely tuned bubble universe, the quantum many-worlds process generates endless branching histories, all the possible stories that can be told with our local laws. But each of those countless quantum branches is just a single thread within our one bubble. Meanwhile, outside our bubble wall, an infinity of other bubbles host their own complete sets of quantum branches, each operating under a different alien physics. It is a staggering vision of reality, an infinite multiverse of infinite multiverses. Your choices here create new timelines, but the stage on which you make them is just one possibility in a cosmic lottery of unimaginable scale. The infinite cosmic lottery of eternal inflation offers one answer to why our universe exists, but it raises a deeper, more unsettling possibility. If every conceivable physical law manifests somewhere in the multiverse, could our specific set of rules, with all its quantum quirks, be something else entirely? This brings us to a theory that reframes reality not as a fundamental layer of existence, but as a product of something else. This is the simulation hypothesis. It proposes that our entire universe, from the largest galaxy to the smallest quantum particle, is not base reality. It is an artificial construct, a sophisticated simulation running on some form of advanced computational substrate. Think of it as the ultimate video game, with physics itself as the game engine. From this perspective, the bizarre rules of quantum mechanics are not mysteries of nature, but features of the code. Quantum superposition, that state where a particle is everywhere and nowhere until observed, starts to make a strange kind of sense. In a complex simulation, rendering every single detail of reality in full high definition at all times would be computationally wasteful, even for an unfathomably advanced civilization. It would be like a video game trying to render every leaf on every tree in a vast forest when the player is not even looking at it. A far more efficient approach is to use a technique called procedural generation or lazy loading. You only calculate and render the details of the world when they are needed, when an observer looks. The famous double-slit experiment, where a particle seems to know if it is being watched, could be seen as a processing shortcut. When no one is measuring which slit the particle goes through, the simulation does not bother calculating a definite path. It just assigns a probability wave. But the moment an observer sets up a detector, the program is forced to commit, to render a concrete outcome and update the state of the simulated world accordingly. This could explain wave function collapse not as a fundamental law, but as a rendering event. The observer effect is not about consciousness creating reality, but about user input forcing the simulation to resolve an uncertain variable. Even the probabilistic nature of quantum events fits this model. To save processing power, a simulation might use pseudo-random number generators for certain outcomes, creating the illusion of true randomness within a deterministic program. So what about the quantum timelines we have been exploring? In a simulation, the many worlds interpretation could represent a system saving every possible state, like a video game constantly creating save files at every decision point. The pilot wave theory might reflect a deeper, deterministic algorithm running beneath the rendered graphics, and the Copenhagen interpretation could simply be our description of the user interface, the rules of how the simulation presents reality to us, the players within it. This leads to a fascinating and slightly eerie question. If this is a simulation, could we ever find evidence of its limits or glitches in the code? Some scientists have speculated that certain constants in physics, like the speed of light, might be artifacts of processing constraints, a maximum clock speed for the cosmos. Others look for anomalies in high-energy particle collisions or strange statistical patterns in cosmic background radiation as potential signs of underlying computational architecture. The most profound implication for our timeline, however, is about purpose and authorship. If our universe is simulated, then our entire history, from the Big Bang to this very moment, is part of a constructed narrative. Your memories, your choices, the branching paths of your life might all be variables within a grand experiment, a work of art, or perhaps something we cannot even conceive. This does not make your experiences less real to you, any more than a character in an incredibly rich novel feels unreal. But it does suggest that the ultimate nature of our reality and all its quantum mysteries might be rooted not in physics, but in something resembling information. It turns the universe from a place into a process, a story being told or a calculation being run. And if our timeline is part of a simulation, who or what is running the program? The simulation hypothesis reframes reality as information, but there is an even stranger interpretation where time itself loses its one-way arrow. This is the transactional interpretation, a theory that suggests quantum events are not settled in the present, but through a bizarre negotiation between the past and the future. Forget particles or waves. Here, reality emerges from a kind of temporal handshake. Imagine you want to send a light signal from a star to a telescope on Earth. In this view, the star does not simply emit a photon that travels blindly through space. Instead, it sends out what is called an offer wave. This wave radiates forward in time, exploring all possible paths to every potential destination in the universe. It is a quantum invitation. When this offer wave finally reaches a suitable absorber, like the telescope's detector, something remarkable happens. The absorber does not just passively receive. It sends a response back through time. This is the confirmation wave, traveling backward along the exact path the offer wave took. Only when the offer wave from the past and the confirmation wave from the future meet in a perfect agreement does a transaction become complete. It is this closed loop, this handshake across time, that creates what we perceive as a real, tangible particle traveling from the star to the telescope. The photon we detect is not a thing that was launched. It is the echo of a completed deal. This introduces a mind-bending concept called retrocausality, where effects in the future can influence causes in the past. In this framework, the present moment is not the sole author of reality. It is more like a middle manager finalizing contracts that have been negotiated between the past's possibilities and the future's needs. The universe is not unfolding from a fixed past into an open future. It is being crystallized from both ends at once. This has a startling implication for our quantum timelines. It means the future is not just a blank slate waiting to be written. It is an active participant in its own creation. When you make a choice, the offer waves of your actions ripple forward into countless possible futures. But those possible futures, through their confirmation waves, are also reaching back to select which version of your present becomes solidified. Your past is not a fixed record. It is the set of all transactions that were successfully completed, chosen in part by absorbers that, from your perspective, have not even happened yet. This turns the linear story of cause and effect into a two-way street. The timeline you experience is the one where all the handshakes line up consistently. So why does reality feel so solid and unchangeable? Because these transactions are incredibly specific and self-reinforcing. They create a consistent history, a single narrative thread where all the quantum deals are closed. But the theory leaves a haunting question dangling. If the future helps choose the past, what does it want? The transactional interpretation paints a universe of temporal handshakes, but it leads to an even more radical possibility. What if observers are not just participants in this cosmic deal-making, but the very reason the deal exists at all? This brings us to John Wheeler's participatory anthropic principle, an idea that pushes the role of consciousness to its ultimate limit. Wheeler, a towering figure in 20th century physics, proposed a staggering vision. He suggested that the universe only comes into being because of observers within it. In his famous phrase, "It is a participatory universe," we are not just here because the universe exists. The universe exists because we are here to observe it. This turns the traditional logic of existence completely on its head. To grasp this, we must revisit a cornerstone of quantum mechanics, but with a twist that bends time itself. Consider Wheeler's own delayed choice quantum eraser experiment, a thought experiment that has since been realized in labs. Imagine a single photon, a particle of light, traveling toward a screen with two slits. As we know, if we do not measure which slit it goes through, it behaves like a wave and creates an interference pattern, a signature of it taking all possible paths. If we place detectors at the slits to catch it in the act, it behaves like a particle and the interference pattern vanishes. Now, here is Wheeler's delayed choice. Let the photon pass through the slits unimpeded. It is now in a state of superposition, having gone through both, but do not let it hit the final screen just yet. Instead, divert its path with a series of mirrors and beam splitters, creating two possible routes to two different final detectors. Crucially, the choice of which final detector to use can be made randomly by a computerized switch after the photon has already passed through the slits and is well on its journey. The results are baffling. If the switch is set to send the photon to a detector that reveals which slit it came through, the photon acts like a particle and no interference is seen. If the switch is set to send it to a detector that erases that which path information, the photon acts like a wave and interference appears. The staggering implication is that our choice of measurement in the present seems to dictate how the photon behaved in the past, long before we made that choice. It is as if the photon, back at the slits, knew what kind of experiment it would encounter in its future and adjusted its behavior accordingly. This is not a mere quirk of equipment. It suggests that a present observation can reach back and influence the past, solidifying one version of history over another. Wheeler took this a step further into the cosmic scale. He applied the same logic to the light from the most ancient quasars, billions of light years away. That starlight has been traveling for eons, and it can be set up to act as a galaxy-sized delayed choice experiment. By how we choose to observe that ancient light today, we might be determining whether it traveled here as a particle taking one definite path, or as a wave taking all possible paths across billions of years. Our observation now could be selecting which of those possible histories actually happened. This is where the participatory anthropic principle crystallizes. If present acts can shape the past, then observers today are not just witnessing cosmic history. We are in some sense authoring it. The Big Bang, the formation of galaxies, the rise of life on Earth. This entire grand narrative may be a tapestry woven from both ends, with our conscious observations now serving as the final stitches that pull the whole picture into coherent existence. We are not discovering a pre-recorded film. We are collaboratively writing the script, and the scenes we write include the prologue. This means your act of observation, of questioning and seeking understanding, is not a passive glance at a finished universe. It is an active, necessary part of bringing that universe into being. In Wheeler's vision, we are all participants in a cosmic act of creation that spans all of time, a closed loop of meaning where the universe generates observers, and those observers, by the very act of seeing, generate the universe that made them. It is a profound and humbling responsibility, casting each of us as essential co-creators of reality itself. Wheeler's participatory universe suggests we help write cosmic history, but what if that history is not even happening where we think it is? This leads us to one of the most profound reimaginings of reality in modern physics, the holographic principle. It proposes a staggering idea that our three-dimensional universe, with all its depth and drama, might be a projection from a two-dimensional surface. Everything you see, touch, and experience, from the farthest star to the memory of your first kiss, could be akin to a hologram. In a hologram, a three-dimensional image is encoded on a flat, two-dimensional piece of film. Shine the right light through it, and a fully formed Chinese letter image pops into view. The holographic principle applies this logic to the cosmos itself. It suggests that all the information needed to describe everything within a volume of space, say a room or an entire galaxy, is not spread throughout that volume. Instead, it is painted like a cosmic fresco on the boundary that surrounds it. For our entire observable universe, that boundary is the distant, spherical shell of the cosmic horizon, the farthest light we could ever hope to see. On that unimaginably distant surface, information is stored in tiny, fundamental units like pixels, but at the scale of the Planck length, the smallest possible size in nature. Our rich three-dimensional reality, with its flow of time and quantum mysteries, is a grand illusion projected from that flat, timeless, two-dimensional code. This is not a metaphor for how we perceive things. It is a serious mathematical result emerging from the study of black holes and quantum gravity. A black hole's entropy, which is a measure of its hidden information, was found to be proportional not to its volume, but to the area of its event horizon, its surface. This hinted that the information about everything that ever fell in was not lost inside, but smeared across that two-dimensional boundary. The holographic principle extends this radical accounting to the entire universe. So what does this mean for our quantum timelines? If our three-dimensional reality is a projection, then time itself, the very stage on which alternate histories play out, may also be an emergent phenomenon. It is not a fundamental feature of the cosmos. In the true two-dimensional code at the boundary, there may be no time as we understand it. Instead, that timeless surface contains all possible configurations, all possible states, like the frames of a film. Our experience of a flowing present, of cause and effect, of a past that is fixed and a future that is open, is what happens when that cosmic film is played, when the holographic projection is activated. From this perspective, the branching quantum timelines of the many worlds interpretation are not separate, parallel universes stacked in some higher dimensional space. They are different sequences, different possible orderings of the frames encoded on the boundary. Your timeline, the one you are living, is one specific projection, one way of reading the data. The version of you that made a different choice is another valid projection from the same underlying code. They are not splitting apart, they are simply different renderings of the same complete library of possibilities. This transforms the nature of reality from a substance into a story, from a place into a process of information becoming experience. The solidity of history, the weight of the past, feels real to us because the projection is coherent and consistent, but it is no more fundamental than the three-dimensional image floating above a holographic plate. The holographic principle offers a strange comfort. It suggests that at the deepest level, the universe is not wasteful or infinitely complex. It is elegantly economical, storing the script for all of creation on the skin of the cosmos. Our lives, with all their branching paths and poignant choices, are part of that magnificent projected story. And if time is not fundamental, then perhaps every moment, every possible version of every event already exists in that timeless code, waiting for an observer to give it the illusion of sequence. This leads us to wonder if we are living in a cosmic hologram. What kind of projector could possibly be running the show? The holographic universe suggests a timeless code, but what if time is not just an illusion but a broken concept from the start? To find a theory that tackles this head-on, we must step away from strings and holograms and into the granular fabric of reality itself. This is loop quantum gravity, a bold and elegant rival to string theory that asks a deceptively simple question. What if space-time is not a smooth, continuous stage, but is made of tiny, indivisible pieces? In this view, the universe is not a place where things happen. At its most fundamental level, it is a network of relationships, a cosmic web woven from threads of gravity. The theory paints a picture of space that is not empty nothingness, but a dynamic fabric composed of finite loops. These loops, at the unimaginably tiny Planck scale, link together to form a flexible quantum mesh. Think of a chainmail tunic. From a distance, it looks like a smooth, continuous surface, but up close, you see it is made of countless interlinked metal rings. Loop quantum gravity proposes spacetime is like that chainmail, a tapestry of woven loops. This structure has a profound consequence. It prevents the infinite, crushing densities predicted by classical physics at the heart of black holes and the Big Bang. Instead of a singularity of zero size, there is a smallest possible unit of space, a quantum of volume. The universe cannot be squeezed smaller than this. This leads to the theory's most mesmerizing prediction, the spin foam. Imagine the history of this quantum spacetime, not as a flowing river, but as a frozen sculpture. A spin foam is a complex, branching network that represents all the possible ways the loops of space can interact and change over what we perceive as time. Each intersection or vertex in this foam is a quantum event, a fundamental transition. The entire foam captures every possible history of the universe, every way the cosmic chainmail could have been woven. Here is where the concept of a timeline begins to dissolve. In many interpretations of loop quantum gravity, time as a fundamental, flowing parameter does not exist in this foundational description. The spin foam is timeless. It is a static, four-dimensional structure that contains all possible configurations of space and their connections. What we experience as the relentless march of time from past to future is not a primary feature of reality. It is something that emerges, like temperature emerging from the chaotic motion of molecules, when you look at this vast network in a particular way. Our conscious experience of a flowing present, of cause and effect, is a story we tell ourselves as we trace a path through this eternal, event-filled sculpture. This challenges the very core of our narrative about reality. There is no single privileged timeline. There is only the complete foam, and within it, every sequence of events that is logically consistent. Your life, with all its memories of a linear past, is one coherent thread woven through this network. The version of you that made a different choice is another valid thread in the same timeless structure. They do not branch away from each other. They simply coexist as different routes through the quantum landscape of all possibilities. In this view, asking what happened before the Big Bang becomes a question framed in the wrong language. If time is emergent, then the Big Bang is not an event in time. It is a particular region or configuration within the spin foam, a place where our emergent concept of time as we know it begins to make sense. Before has no meaning in the timeless foundation. We are left with a universe that is, at its heart, a vast and silent network of quantum relationships. Our journey from birth to death, the rise and fall of civilizations, the dance of galaxies, all of it is a single, frozen possibility within an immense static tapestry. We do not move through time. We are, each of us, a timeless pattern within the foam, and the sensation of moving is the pattern itself being read. The frozen tapestry of loop quantum gravity offers no branching paths, only a single timeless sculpture of all possibilities. But what if our timeline is not just self-consistent, it is actively protected from contradiction? This brings us to a principle that tackles the ultimate puzzle of time travel, the Novikov self-consistency principle. It proposes a universe that is fundamentally immune to paradox, where the past cannot be changed because it already includes your future attempts to change it. Imagine traveling back in time to prevent a famous historical event. You arrive with your modern knowledge and technology, fully intending to alter the course of history. But according to Novikov, you will fail. Not because of gods or bad luck in a classical sense, but because the universe itself will orchestrate a series of seemingly random quantum-scale events to ensure your actions only bring about what has already happened. Your attempt to prevent the event will be the very cause of it. A classic illustration is the billiard ball scenario. Suppose you have a time machine that sends objects 5 minutes into the past. You set up a billiard table with a hole in the center. Your plan is to send a billiard ball back in time so it emerges from the machine and knocks its past self off course, preventing it from ever entering the time machine in the first place. This is the grandfather paradox in miniature, a logical loop that should erase its own cause. Novikov's principle says this cannot happen. Instead, what you would observe is a bizarre series of events. The ball rolls toward the time machine. Just before it enters, an unseen force, a gust of air or a tiny vibration of the table, gives it a slight nudge. This microscopic change, a quantum fluctuation, alters its path just enough so that when it emerges from the past, it does not hit its past self with enough force to knock it away. It might glance off it or miss entirely in a way that still allows the original sequence to proceed. The universe, through an infinite number of such subtle adjustments across all quantum probabilities, guarantees consistency. Your timeline is not a thread you can snap. It is a Möbius strip, a single, closed loop where every event, including your time-traveling meddling, is a locked piece of the puzzle. This transforms free will in a profound way. You retain the feeling of choice, the intention to change things, but any action you take in the past was always a part of that past. You were always there. The history books in this single, rigid timeline have quietly included your presence all along. Your great-grandfather survived not despite your trip to the past, but because of some accidental, seemingly random action you took while there. The universe is not passive. It is an active editor, redacting contradictions before they can be written, enforcing a story that makes sense from beginning to end. This suggests a cosmos where time travel, if it is ever possible, would not be a tool for alteration, but a mechanism for revelation, showing us that we were always part of a predetermined, self-healing script. The Novikov principle locks history into a single, unchangeable loop. But what if the branching we sense is not out in the cosmos at all? What if it is happening inside your own skull? This is the many minds interpretation, a profound twist on the classic many worlds idea. It proposes that the universe itself does not split. Instead, your mind does. In this view, there is only one unchanging quantum reality, a single, vast wave function that contains all possible outcomes in a state of superposition. The branching occurs not in the fabric of space-time, but in the fabric of consciousness itself. When you perform a quantum measurement, like observing Schrödinger's cat, the universal wave function does not fracture into separate worlds. It remains whole, containing both the alive cat and the dead cat in a single, coherent state. But your consciousness, your awareness, cannot hold both contradictory facts at once. So it splits. One stream of awareness perceives a living cat. Another, completely separate stream of awareness, housed in what is physically the same brain, perceives a dead cat. Both minds exist, but they are now isolated from each other, each experiencing a different facet of the one true reality. You are not in two places at once. Your awareness is simply following one thread of a vast, tangled tapestry. blind to the other threads woven from the same material. This radically redefines what we mean by self and identity. In the standard many worlds view, a new copy of you is born with every quantum decision, a separate person in a separate universe. In the many minds view, there is only one physical you, one body, one brain. But that single brain can host multiple, non-communicating streams of conscious experience. Each stream feels like the real you, with a continuous memory of a single, linear history. From the inside, it feels exactly like living in one branch of a multiverse. But from the outside, from a God's eye view of the quantum state, all those yous are just different modes of awareness flickering within one physical system. This leads to a haunting philosophical question: which mind is the true you? If both streams of experience originate from the same neural substrate, are they equally valid instances of your identity? It suggests that personal identity is not a singular, enduring thing, but a process, a momentary vantage point taken by a much larger and more complex cognitive structure. Your sense of a unified self, of being one person on one timeline, is an illusion created by the fact that these mental streams do not communicate. You only ever experience one at a time. The other you, the one who saw the opposite outcome, is just as real to itself, but it is forever separated from you by a wall of subjective experience. This interpretation elegantly sidesteps some of the more extravagant metaphysical claims of many worlds. There is no need for an ever-inflating cosmos of duplicate planets and galaxies. The extra reality is all in the mental realm, a proliferation of perspectives rather than matter, but it places an immense weight on consciousness as the fundamental separator of realities. The universe is whole, but we, as observers, are forever fractured, each shard of awareness illuminating a different slice of the quantum whole. It means that at this very moment, other minds that share your name and your memories are experiencing different versions of this sentence, different conclusions to every uncertain event around you, all from within the same silent, physical universe. The many minds view suggests our awareness fractures to perceive a whole universe, but what if the opposite is true? What if the universe itself is performing a kind of natural selection, choosing which possibilities become solid for everyone to see? This is the theory of quantum Darwinism, a powerful idea that explains how the fuzzy quantum world gives rise to the single, stable reality we all agree on. It proposes that the classical world we perceive is not an illusion, but the result of a relentless copying process where only the most robust quantum information survives. Think of a quantum particle like an electron in a state of superposition. It is not here or there, but in a blend of locations. According to quantum Darwinism, this delicate state is constantly bombarded by its environment. Every passing photon, every stray air molecule, even the faint whisper of the cosmic microwave background interacts with it. These interactions are not deliberate measurements. They are simply the universe bumping into itself, but each bump, each tiny interaction, takes a little piece of information about the particle and copies it. It is like a secret being whispered from one person to the next in a vast crowd. Crucially, not all quantum states are created equal in this noisy environment. Some states are fragile, like a house of cards, and collapse instantly when disturbed. Others are incredibly robust, like a diamond. They can withstand the constant pummeling from the environment without being destroyed. These robust states are called pointer states, and here is where the Darwinian selection happens. The environment acts as a ruthless editor. It continuously and randomly samples the quantum system. The fragile states get scrambled and lost in the chaos, but the robust pointer states, they survive. More than that, they get replicated. Their information is copied over and over again, spreading into the environment like a meme going viral. Soon, countless fragments of the environment, from the dust in the air to the light in the room, all carry the same consistent information that the electron is, for instance, definitely here and not there. This is how the quantum becomes classical. You, as an observer, do not need to perform a special, magical act of measurement to collapse reality. You simply come along and sample a tiny piece of that environment. Because the information about the pointer state has been copied everywhere, you easily access it. You look at the dust, the light, the air, and they all tell you the same story. This consensus defines objective reality. We all see the same world because we are all tapping into the same, widely copied environmental records. The branching timelines of pure quantum possibility are pruned away by this process. Only the histories that produce stable, copyable pointer states leave a lasting record in the world, a record we can all read and agree upon. In this view, the timeline we share is not the only one that was ever possible. It is the one that was most fit to survive the brutal process of being constantly observed by the cosmos itself. Our reality is not a private hallucination. It is a public broadcast selected for its durability and copied onto the very fabric of the world around us. Quantum Darwinism shows us a reality selected for durability, a consensus broadcast. But what if the receiver of that broadcast, our own consciousness, is itself a quantum phenomenon? This brings us to one of the most audacious and controversial ideas at the edge of science, the Or theory, proposed by physicist Roger Penrose and anesthesiologist Stuart Hameroff. Their theory suggests consciousness is not a mere byproduct of classical brain computation. It is a direct manifestation of quantum physics playing out inside our neurons. At the heart of their proposal are structures called microtubules. These are tiny, cylindrical scaffolds inside every neuron, part of the cell's skeleton. For decades, neurobiology viewed them as simple structural supports, like microscopic bones. But Penrose and Hameroff saw something else. They proposed that these microtubules are perfectly sized and organized to protect delicate quantum states. Within their hollow cores, electrons could become quantum entangled, existing in a superposition, a blend of possibilities shielded from the disruptive noise of the warm, wet brain. This is where Penrose's unique insight comes in. He argued that understanding consciousness requires a new kind of physics, one that bridges the gap between the quantum and classical worlds. He pointed to Gödel's incompleteness theorems in mathematics, which suggest that true understanding, genuine insight, is non-computable. A standard computer following an algorithm can never achieve it. Penrose believed that human consciousness, with its capacity for genuine understanding, creativity, and free will, must therefore be non-computable as well. He proposed that the missing ingredient is quantum gravity, the still unknown theory that would unite Einstein's relativity with quantum mechanics. In the Or model, the superposition of states within the microtubules grows until it reaches a threshold related to quantum gravity. At that precise moment, the superposition collapses, not randomly as in standard quantum theory, but in a non-computable way dictated by the geometry of spacetime itself. Each collapse is a moment of conscious experience, an orchestrated objective reduction, which gives the theory its name, Or. Each flicker of awareness is a tiny quantum gravitational event. Now connect this to our exploration of timelines. If our conscious choices are born from these non-computable quantum collapses in the brain, then our decision-making process is not a deterministic calculation. It is a unique navigation through the landscape of possibilities. In the many worlds picture, every quantum possibility becomes real in some branch. But the Or theory suggests our conscious mind, via these gravity-influenced collapses, might selectively tune into one branch over another. It is not that we create a new timeline with every thought. Rather, our quantum-aware consciousness might act as a resonance filter, aligning our experience with one specific thread in the multiverse that resonates with our intent or understanding. Imagine standing before a choice, feeling the weight of possibilities. According to this view, the quantum superpositions in your brain are not just reflecting those possibilities, they are interacting with them. The non-computable collapse then selects a future that is consistent with a deeper, perhaps aesthetic or meaningful, geometry of reality. Your free will is not an illusion of chemistry, but a genuine quantum gravitational phenomenon, a gentle steering through the foam of possibilities. This paints a breathtaking picture where your innermost moments of awareness are direct conversations with the fabric of space-time, and your life's path is a melody orchestrated by the universe's most fundamental forces. Of course, this theory is hotly debated, with many physicists questioning whether quantum coherence can survive in the noisy environment of the brain. Yet it stands as a profound attempt to place us, our minds, directly into the quantum narrative of reality. It suggests we are not passive observers of a branching multiverse, but active participants whose very consciousness is woven from the threads that might bind those branches together. If true, then each moment of understanding, each flash of insight, is a tiny singularity where the quantum world and the gravitational world meet to write the next line of your story. Einstein's own vision of reality offers a perspective so radical it makes time travel seem mundane. His theory of relativity did more than link space and time. It suggested that our most intimate experience, the flow of moments from past to future, is a profound illusion. This is the block universe theory, where all of existence is a single, frozen, four-dimensional sculpture. In this view, the past is not gone, the future is not unwritten. Every event that has ever happened or ever will happen exists eternally, laid out along the dimension of time just as objects are laid out in space. Your birth, your first words, this very moment, and your last breath, they are all equally real, fixed points in an immense cosmic block. Think of a movie on a DVD. The entire story is present on the disc from start to finish. When you play it, you experience a flowing narrative, a sequence of cause and effect. But the DVD itself does not change. All the frames coexist. The block universe proposes our reality is like that complete DVD. We are not watching the film, we are characters within it, and our consciousness is like the laser reading the disc, illuminating one frame at a time and creating the compelling, inescapable sensation of a moving present. This reshapes every quantum mystery we have explored. From within the block, quantum probability looks very different. That famous uncertainty, the idea that a particle's path is not determined until measured, might simply reflect our limited viewpoint. We are like a reader who can only see one word of a novel at a time. To us, the next word seems uncertain, a matter of probability, but the entire book is already written. All possible outcomes of a quantum experiment are not branching into new realities. They are simply different parts of the pre-existing block, and our journey through it makes us encounter one specific version. The many worlds in this framework are not separate universes splitting apart. They are all part of the block's intricate geometry, like different strands woven through the same tapestry. Your timeline and all its alternate versions where you made different choices are all equally real and unchanging threads in this eternal whole. The feeling of making a choice, of free will, is the experience of traversing a path that was always there. This leads to the theory's most haunting implication. The passage of time, with its urgency and poignancy, is not a feature of the cosmos. It is a psychological artifact, a trick of consciousness. Our brains are wired to construct a narrative, to string together moments in a line and remember one direction as past and anticipate another as future. But in the silent block, there is no now that is more real than any other moment. The dinosaurs are just as real as the distant galaxies whose light has not reached us yet. All is simply here in the vast, still expanse of space-time. This can feel disorienting, even bleak, as it seems to rob our lives of genuine becoming. Yet it also offers a strange kind of solace. In the block, nothing is ever lost. Every moment of joy, every act of love, every triumph and failure exists forever, etched into the structure of reality. Your story is not fleeting. It is a permanent fixture of the universe, an indelible part of the greatest story ever told. The block universe freezes all moments in a four-dimensional sculpture. But what if the connections within that sculpture are more literal than we ever dreamed? Deep within the mathematics of string theory lies a conjecture so elegant it blurs the line between information and geometry, known as AR equals EPR. It proposes a stunning equivalence that two seemingly different concepts are, in fact, two sides of the same cosmic coin. On one side, we have EPR, named for Einstein, Podolsky, and Rosen, representing quantum entanglement. This is the spooky action at a distance that so troubled Einstein, where two particles become linked so intimately that measuring one instantly determines the state of the other, no matter how far apart they fly. On the other side, we have ER, named for Einstein and Rosen, representing an Einstein-Rosen bridge, the formal name for a wormhole, a hypothetical tunnel through spacetime connecting two distant points. The conjecture boldly states that these are not just analogous, they are identical. Every pair of entangled particles is not just mysteriously linked by information, they are physically connected by a microscopic wormhole, a bridge so tiny it exists at the Planck scale, far beyond our current ability to see. Think of it this way: you and a friend each hold one end of a long, flexible tube. You can be miles apart, yet anything whispered into one end is heard at the other instantly. The tube is the connection. AR equals EPR suggests that entangled particles are like you and your friend, but the tube is a wormhole woven from the fabric of spacetime itself. The spooky action is not action through space, it is information traveling through a shortcut. This transforms our understanding of the quantum world from a realm of abstract probabilities into a landscape of unimaginable geometry. If every quantum entanglement creates a tiny wormhole, then the universe at its most fundamental level is not a collection of separate points. It is a dense, dynamic web of bridges, a cosmic neural network where every connection is a thread through the substrate of reality. Now expand this idea to the scale of the multiverse. In the many worlds interpretation, every quantum decision spawns new branches. According to ER equals EPR, those branches might not just split and drift apart. They could remain tethered, connected by these microscopic spacetime tunnels. The entire quantum multiverse, with its infinite timelines, would then resemble a single, vast organism, its countless possible histories linked in a complex, ever-evolving web of wormholes. Your timeline, the specific path of experiences you call your life, would not be a lonely thread in the void. It would be one route through this immense, interconnected labyrinth. The choices you make might determine which bridges you traverse, which connections become strongest, guiding you along one coherent path through the network. This paints a breathtaking picture where the past, present, and future of all possibilities are not just abstractly related, but physically woven together. The fabric of reality is not a smooth sheet. It is a quantum foam of unimaginable complexity, with every potential event linked to every other by a network of tunnels too small to perceive. In such a cosmos, time travel and communication across branches are not ruled out by principle, but might be constrained by the stability and size of these bridges. A microscopic wormhole linking two entangled particles is useless for sending a person, but it is a fundamental stitch in the tapestry. Could larger, more stable wormholes, the kind of science fiction, correspond to some profound, macroscopic entanglement in the multiverse? The conjecture invites us to see the universe not as a container for things, but as a living fabric of relationships where every quantum link is a literal stitch in spacetime, binding all possibilities into one inseparable whole. But if every quantum link is a stitch in spacetime, what happens when those stitches loop back on themselves? This is the radical domain of retrocausality, a direct challenge to the most fundamental rule of our experience, the arrow of time. Here, the future is not a blank page waiting to be written. It is an active author reaching back to influence its own past. This is not science fiction, but a serious interpretation of quantum mechanics that suggests causation can flow in both directions. The evidence comes from some of the strangest experiments ever conducted, like the quantum delayed choice experiment we touched on earlier, but seen through a new lens. In that experiment, a photon's behavior at a pair of slits seems to be determined by a choice made about how to measure it after it has already passed through. From a retrocausal perspective, this is not a paradox. It is a simple, if mind-bending, fact. The measurement choice in the future sends a signal backward in time, telling the photon how to behave in the past. It is as if a detective, by deciding to look for fingerprints tomorrow, causes those fingerprints to appear on the murder weapon yesterday. The future decision completes a loop, solidifying one version of history over another. This creates a timeline that is not a straight line from past to future, but a closed loop, a self-fulfilling prophecy woven into the fabric of reality. Your present actions could be shaped in part by necessities that have not yet occurred. A scientist might design an experiment today because of a brilliant insight she will have next week, an insight that only became possible because of the data from the experiment she just designed. The loop feels impossible, yet it is perfectly consistent, free of paradox. The universe simply ensures all the pieces fit. This causal logic redefines destiny. Your life's path might not be a trail you blaze into an unknown wilderness. It could be more like a sculpture you are revealing, where the final form in the future guides each chisel strike in the past. The timeline you remember is the one where all these backward and forward whispers align into a single, coherent story. Retrocausality bends time into loops, but what if the universe is not just telling a story, it is solving a problem? This leads us to a breathtakingly speculative theory, the idea that the entire multiverse functions as a quantum computer. In this view, reality is not a place or a substance, but a process, a cosmic calculation unfolding across every possible branch of existence. Each quantum decision point, each moment of superposition, represents the machine exploring a different computational path. Our perceived timeline, the one we experience as solid and singular, is simply the output where all the calculations line up to produce a consistent, stable answer. Think of a computer trying to solve a complex maze. A classical computer would try one path at a time, hitting dead ends and backtracking. A quantum computer, however, could explore all possible paths simultaneously through superposition. It would not choose one route, it would process every route at once, and the final answer would be the successful path out of the maze. Now scale that up to include everything. The Big Bang might be the initialization of the program. The fundamental laws of physics are the operating code. Every particle interaction, every stellar fusion, every chemical reaction in a leaf or a brain is part of the computation. And the many worlds of quantum mechanics are not wasted copies, they are essential processing threads. Every time a quantum system faces a probabilistic outcome, the cosmic computer does not discard the other possibilities. It forks its process, creating new branches to continue the calculation along every potential line. This means the version of you reading this is living in one specific computational thread, one that has remained internally consistent from the first nanosecond after the Big Bang to this very moment. The other yous in other branches are living in different computational threads, solving for different sets of variables and experiences. They are not illusions, they are other valid runs of the program. This elegantly blends the simulation hypothesis with the hard physics of quantum mechanics. We are not necessarily in an artificial simulation created by some higher intelligence, though that remains possible. Instead, the universe might be computational at its very core. Reality is not like a computation, it is a computation with space-time and matter as its hardware, and the quantum wave function as its software. The strange phenomena we have explored, from superposition to entanglement, are not bugs. They are features of this ultimate processing architecture. Entanglement is a form of quantum parallel processing where distant particles share information instantly to solve part of the calculation. The holographic principle, where a three-dimensional universe is encoded on a two-dimensional surface, fits perfectly as a form of cosmic data compression. So what is the universe computing? What is the question to which our reality is the answer? This is the profound mystery at the heart of the idea. Perhaps it is calculating its own existence, a self-consistent set of mathematical truths. Maybe it is exploring every possible form of beauty, complexity, or consciousness. Or it could be solving for stability, for structures that can persist and create ever more intricate patterns within the chaos. Our timeline, with its galaxies, planets, and living beings, might be one particularly elegant and stable solution that the computation has found. This reframes our place in the cosmos. We are not accidental passengers in a meaningless void. We are active participants in a computation of unimaginable scale, momentary flashes of awareness within a processing thread that has computed its way to creatures who can wonder about the nature of the process itself. Our curiosity, our drive to understand the universe, might not be a side effect. It could be a feature of the program, a way for the computation to become self-aware, to observe and reflect upon its own magnificent output. A cosmic computer calculating every possibility is a staggering vision, but what if we could feel the edges of those other calculations? What if the cracks between timelines sometimes show? This brings us to a strange and deeply personal mystery, the Mandela effect. It describes a peculiar phenomenon where large groups of people share a specific, detailed memory of a past event that, according to all records, never happened. The name comes from the most famous example, where thousands vividly recall news coverage of Nelson Mandela dying in prison in the 1980s, despite his actual release and presidency. For many, this is not a simple mistake. It is a bone-deep certainty that clashes with documented reality. Psychologists offer compelling explanations like confabulation or the social spread of false memories. Our brains are imperfect recorders, prone to filling gaps with plausible details that then feel as real as any genuine memory. Yet, on the wilder shores of speculation, a more radical explanation whispers. Could these shared false memories be psychic residue from a timeline that once was or still is, but is not this one? In the quantum multiverse, every decision spawns new branches. Most branches diverge wildly, creating entirely different worlds, but some might be quantum neighbors, differing by only the tiniest of details: the spelling of a children's book title, the design of a corporate logo, the line from a famous movie. The fringe theory suggests that our conscious awareness is not perfectly locked to a single timeline. Perhaps through a process we do not understand, information, or even the faintest echo of experience, can bleed between these closely related branches. You might have a strong memory of the Berenstain Bears books being spelled Berenstein, because in a neighboring branch of the multiverse that is the correct spelling. In this branch, it is Berenstein. The memory feels real because in a very real sense it is. It is a ghost image from a reality that is almost identical to ours, a quantum afterglow. This idea transforms the Mandela effect from a curiosity about faulty memory into a potential signpost of the multiverse's architecture. It suggests that the walls between worlds are not always perfectly opaque. Under certain conditions, maybe during states of collective focus or through some unknown quantum resonance, a subtle crosstalk occurs. We are not remembering something that never happened. We are faintly perceiving something that did happen, just not here. Think of it like hearing a faint radio broadcast from a distant city on the same frequency as your local station. For a moment, two signals overlap. The static you hear is the interference pattern between two nearly identical realities. The famous movie line, "Luke, I am your father," is misremembered by millions because in a nearby timeline, Darth Vader actually said it that way. Our timeline settled on the more grammatically correct "No, I am your father." The emotional core of the scene is identical, but the precise words differ. To those who carry the echo, the discrepancy feels jarring, a glitch in the matrix of their personal history. This theory is, of course, untested and sits far outside mainstream science. It is impossible to prove and easy to dismiss, yet it serves a powerful purpose. It takes a shared human experience, that eerie feeling of collective misremembering, and uses it as a lens to view the quantum landscape. It asks us to consider that the past is not a fixed monument, but a fluid narrative, and that our sense of history might be more porous, more interconnected with other possibilities than we ever dared to believe. The Mandela effect, in this light, is not proof of the multiverse, but a story we tell about the unsettling feeling that our timeline might not be the only one we have ever known. If our observation can reach back and shape the past, could it also lock the present into place? There is a quantum phenomenon that suggests exactly that, a mechanism where the simple act of looking holds reality still. This is the quantum Zeno effect, named after the ancient Greek philosopher Zeno of Elea, who proposed a paradox that motion is impossible because to move from one point to another, you must first cross half the remaining distance and then half of that, and so on, resulting in an infinite number of steps you can never complete. In the quantum world, this philosophical puzzle becomes a startling physical reality. The effect states that if you observe an unstable quantum system rapidly and repeatedly, you can effectively prevent it from changing or decaying. It is not that you are repairing it with your gaze, you are resetting its clock. Imagine a radioactive atom poised to decay. Left unobserved, its quantum wave function will evolve, and within a predictable time, it will likely spit out a particle and transform. But if you bombard that atom with a series of quick, successive measurements, asking over and over again, "Are you still in your initial state?" something remarkable happens. Each measurement forces the system to collapse back into that initial state, like a student caught not paying attention who snaps back to looking at the textbook. The natural evolution of the system is interrupted, its probability of decay reset to zero again and again. With enough observations per second, the atom can be kept in its original form almost indefinitely, frozen in time by the relentless spotlight of measurement. This has been demonstrated in laboratories, not with atoms decaying, but with particles transitioning between states. By watching them continuously, scientists have literally stopped a quantum system from making a jump it was desperate to make. Now take this concept and expand it to a cosmic, philosophical scale. We have discussed the participatory anthropic principle, the idea that observers are necessary to bring the universe into concrete existence. The quantum Zeno effect could be the precise mechanism that makes this participation permanent. What if our continuous observation, the collective gaze of every conscious being across time, is not just revealing reality but actively pinning it down? Each moment of awareness, each conscious registration of the world around us could be acting as a measurement, a cosmic check-in that says, is the universe still here, still following these rules, still containing this timeline? And with each check, the wave function of possibility collapses back into the familiar, stable reality we know. In this view, our timeline is not the only one that could have existed. It is the one that has been perpetually observed into stability. The countless other quantum branches, the alternate histories where things played out differently, may have flickered into potential, but without a sustained observer to lock them in, they faded back into the quantum foam. Our particular cosmic story, with its specific laws and consistent history, is the one we have all been watching and thus freezing since the dawn of consciousness. This paints a picture where life is not a latecomer to a pre-formed universe. It is an essential component, the glue that holds a particular version of existence together. Our relentless collective observation acts as a kind of temporal anchor, a Zeno effect on a grand scale, preventing our reality from devolving into chaos or branching away into oblivion. It suggests that the solid ground beneath our feet, the predictable sunrise, the reliable flow of time, are not guaranteed by physics alone. They are maintained by a silent, continuous act of participation from every seeing thing within it. The universe persists because we are here to see it, and we keep looking. The relentless gaze of observation might pin our reality in place, but what breathes life into the relentless arrow of time itself? The answer may lie in a process more fundamental than measurement, a quiet, universal interaction called decoherence. This is the silent whisper that turns the quantum world's shimmering potential into the solid, classical reality we navigate every day. Decoherence explains how the fragile state of superposition, where a particle can be in two places at once, inevitably crumbles when that particle bumps into the messy, bustling world around it. It is not a conscious observer that collapses possibilities, but the environment itself, acting as a relentless, chattering witness. Imagine a perfectly still pond, its surface like a mirror. This represents a quantum system in perfect isolation, in a pure state of superposition. Now toss a single pebble into its center. The ripples that spread out are clean, coherent, and predictable. This is the undisturbed quantum wave, but our universe is not a still pond. It is more like an ocean during a storm. Now throw that same pebble into the churning waves. Its tiny splash is immediately lost, swallowed by the immense, chaotic motion of the water. The information about the pebble's impact gets scrambled into the vast thermal noise of the sea. This is decoherence. The quantum system, our pebble, interacts with the infinite number of degrees of freedom in its environment, the countless water molecules. Its delicate quantum phase information, the thing that allows for interference and superposition, leaks out and becomes irretrievably lost in the chaos. Once this happens, the system can no longer exhibit quantum weirdness. It behaves classically. It is definitively here or there. The magic is gone, not because anyone looked, but because the universe is too loud to ever be truly quiet. This process is why we do not see cats that are both alive and dead, or footballs in two places on the field. Large objects, and even small ones in warm environments, are constantly bombarded by photons, air molecules, and gravitational fields. They decohere almost instantaneously, trillions of times per second, locking them into a single, definite state. So where does time come in? Decoherence provides a powerful arrow, a directionality that the underlying quantum laws do not possess. At the fundamental quantum level, the equations are time-symmetric. They work just as well running backward as forward. There is no inherent past or future. But decoherence is a one-way street. Information, once scattered into the environment, cannot be neatly gathered back up. You cannot unscramble an egg. You cannot unring a bell. The quantum coherence once lost is lost forever in the thermodynamic rise of entropy. This irreversible leakage of information from a system into its surroundings is what creates the psychological and physical arrow of time we experience. Our perception of time flowing from past to future is the sensation of decoherence happening everywhere, all at once, forever. Each moment, the universe becomes a little more classical, a little more definite, a little less quantum. The past is the set of events that have irreversibly decohered, their quantum possibilities solidified into a fixed record imprinted on the environment. The future is the realm of quantum potential that has not yet interacted, not yet been forced to choose. Our timeline, then, is not a pre-written script or a branching tree. It is the one consistent history that has successfully decohered from the quantum soup of all possibilities. It is the path of least resistance through the noise, the story that left the clearest, most durable imprint on the cosmos. Every choice you make sets off a cascade of interactions that decoheres one specific future into the solid past, while letting the other possibilities fade back into the quantum haze. not because they are unreal, but because they failed to leave a lasting mark on the universe's relentless memory. We are not walking through a garden of forking paths. We are surfing a wave of decoherence, riding the leading edge where quantum potential crystallizes, moment by moment, into the unchangeable stone of history. Decoherence carves our single history from the quantum haze, but what if that history is already complete? The block universe, that four-dimensional sculpture where all of time exists at once, presents a profound stillness. Yet quantum mechanics is all about shimmering potential and choice. Can these two visions, one frozen and one fluid, ever be reconciled? A compelling synthesis exists, merging the static B theory of time with the dynamic heart of quantum mechanics. In this view, quantum superposition does not describe a particle in flux. It describes a menu of static realities. Every possible outcome of a quantum event is not a maybe waiting to happen. It is a definite fact within its own complete four-dimensional block. The famous cat is not both alive and dead in one fuzzy reality. There are two perfectly solid, fully realized block universes, one with a living cat and one with a dead cat. Both exist eternally. They are not side by side in space, but as complete and separate timelines within a grander multiverse. From this perspective, the act of measurement is not a magical collapse that destroys possibilities. It is a moment of alignment. Your observation does not create a single reality. It synchronizes your conscious awareness with one specific block, locking your stream of experience onto that single, unchangeable track. Imagine walking into a vast library where every book contains the full, detailed history of a universe. Each volume is a block universe, complete and finished. One book tells the story of a world where you turned left this morning, another where you turned right. They are both written, bound, and sitting on the shelf. Your life as you experience it is not the process of writing a story. It is the process of reading one. The moment you make a choice or observe a quantum event, it feels like you are deciding the plot. But in this merged theory, you are simply opening a book to the next page, and the act of looking confirms which volume you have been holding all along. This elegantly resolves the tension between a timeless cosmos and our experience of flow. The flow is real to us because consciousness is a process that moves through the block, reading its contents in sequence. Quantum probabilities we calculate are not odds of something becoming real, but odds of which pre-existing block our awareness will next inhabit. This transforms the multiverse from an ever-splitting tree into a vast, timeless library. Every story that could be logically told is already on the shelf. Our journey is one of navigation, not creation. We are not authors of our timeline, but explorers within an infinite archive of all possible histories, each one as concrete and unchanging as a novel. The library of timeless blocks presents a cosmos of finished stories, yet our deepest cosmological theories suggest the story may not have a true beginning or end. There are models where the universe is not a single volume, but a chapter in an endless, repeating saga. This is the realm of the ekpyrotic and cyclic models, visions of a cosmos reborn from its own ashes through collisions in a hidden, higher dimensional space. Here, our Big Bang was not a singular creation event, but a violent, transformative encounter. The theory emerges from string theory, which posits that the fundamental constituents of reality are not point-like particles, but tiny, vibrating strings. A key feature of this framework is the existence of extraspatial dimensions, curled up so small we cannot perceive them. Within this landscape, our entire three-dimensional universe could be a membrane, or brain for short, floating within a higher dimensional bulk. Picture our cosmos not as an expanding balloon in nothingness, but as a vast flat sheet, like an infinite page floating parallel to another infinite page in a higher dimensional volume. The ekpyrotic scenario proposes that our Big Bang was the result of a collision between two such brains. They drifted toward each other in the dark of the bulk, and when they met, the impact released an unimaginable torrent of energy, heating our brain to incredible temperatures and setting off the expansion and evolution we call our universe. The cosmic microwave background, the afterglow of the Big Bang, could be the cooled remnant of that colossal brain collision, but the story does not end with expansion. In some cyclic versions of this model, the dance continues. After the collision, the brains bounce apart, stretched and energized. The universe we live in expands, cools, and forms galaxies just as we see. But eventually, dark energy might weaken, gravity might reassert its pull, and the expansion could slow, halt, and reverse. Galaxies would hurtle together, stars and planets would be crushed, and all matter would converge toward a final, ultra-dense state, a big crunch. Yet instead of ending in a singularity, that immense density and heat could provide the force to repel the brains in the higher dimension once more, setting them up for another slow drift and eventual collision, sparking a new Big Bang. In this breathtaking vision, our universe is just one cycle in an infinite, timeless sequence. Each cycle begins with a bang from a brain collision, expands and evolves, then contracts and crunches, only to be reborn again in a new fiery collision. There is no first universe and no last. There is only the eternal, rhythmic dance of creation and destruction. This leads to a profound question about our quantum timelines. If information is never truly lost, as quantum mechanics suggests, could something persist through the apocalyptic fire of a big crunch and the rebirth of a new cycle? Could quantum information, the specific pattern of entanglement and superposition that defined our universe, be transferred or imprinted onto the next? Imagine the history of a cycle, all its stars, planets, and conscious life being compressed into that final, searing density. In the cyclic model, that information might not be erased. It could be scrambled, transformed, but somehow encoded into the initial conditions of the next brain collision. The new universe would not be an exact copy, but it might carry faint echoes of the old. The fundamental constants might be slightly different, the arrangement of matter might vary, but some deep quantum signature of the previous cycle could remain. In a sense, the timelines of each cycle could be linked not as continuous narratives, but as iterations in a cosmic algorithm, each one informed by the one before. Your existence in this cycle, with all its branching quantum possibilities, might be one variation on a theme that has played out infinite times before, in universes with different laws and different stories, yet all born from the same eternal, colliding rhythm of the brains. It suggests that our search for origin may be circular, and our timeline, for all its unique detail, could be a verse in a song that has no beginning and will never end. The eternal cycles of colliding brains suggest a cosmos without end, yet they still describe a reality that exists out there, independent of us. But what if the most radical truth is that quantum reality is not out there at all? What if it resides entirely within the map you use to navigate the world? This is the startling premise of quantum Bayesianism, or cubism, an interpretation that dissolves the paradox of measurement by declaring that quantum probabilities are not features of the world but features of you. They are not objective truths waiting to be uncovered. They are subjective degrees of belief, personal betting odds you assign to future experiences. In this view, the entire mathematical formalism of quantum mechanics is not a description of nature's hidden machinery. It is a user manual, a tool for you, the agent, to make better predictions about what will happen to you when you interact with the world. The wave function is not a physical field spread across space. It is a personal catalog of your expectations, a quantified expression of your uncertainty. When you perform a quantum measurement, you are not collapsing a universal wave function. You are having a private experience, and that experience forces you to radically update your personal catalog, your internal set of betting odds, to account for the new, surprising data. This transforms every quantum mystery into a story about information and personal perspective. Take Schrödinger's cat once more. In cubism, there is no cat that is both alive and dead in any objective sense. There is only you, the agent outside the box, who must assign probabilities to your future sensory experiences. Based on the setup, your best bet is a 50% chance you will see a live cat when you open the box, and a 50% chance you will see a dead one. The wave function you write down encodes these personal odds. The moment you lift the lid and see the outcome, you are not causing a universe to split or a cat's fate to crystallize. You are simply receiving new, decisive information that updates your beliefs from a state of uncertainty to a state of certainty. The cat was always definitively one or the other, but you did not know which, and quantum mechanics was the tool you used to grapple with that ignorance. This makes reality at the quantum level deeply and fundamentally personal. Your quantum reality is not the same as mine until we compare notes. Before we communicate, the outcome of an experiment is a personal experience for each of us, updating our own internal wave functions. Only when we talk, when we share our results, do our subjective realities come into alignment, forging a shared story about the world. In this framework, the famous spookiness of quantum entanglement loses its eerie, action at a distance quality. If two particles are entangled and you measure yours, you instantly update your beliefs about what you will find when you later measure the other, or what your friend will find when they measure it. But nothing physically travels between the particles. You are simply using the quantum tool, the mathematics of entanglement, to correctly anticipate how your future experiences will correlate with events happening elsewhere. The update is in your head, not in the fabric of space-time. This has a profound implication for our understanding of timelines. In cubism, there is no single objective timeline of quantum events unfolding in the world. Instead, there is a tapestry of personal timelines, each one a thread of experience and belief updating for every conscious agent in the cosmos. My history of quantum measurements is a sequence of personal belief updates that makes sense to me. Your history is your own. They are different narratives until we find points of intersection, moments of shared experience where we can synchronize our stories. The solid, classical world we all agree upon emerges not because it is fundamentally real in a quantum sense, but because we are constantly communicating, constantly comparing our personal belief catalogs, and in that social process we build a consensus reality. The chair you are sitting on feels solid and objective because countless interactions and communications have reinforced a consistent set of beliefs about it across all observing agents. Cubism places you, the experiencing individual, at the very center of the quantum narrative. It says the universe does not impose a reality upon you. You use the superb tool of quantum mechanics to navigate a world that is inherently unpredictable to you, and in doing so, you author your own unique thread of understanding. Your timeline is not a path through a pre-existing landscape. It is the evolving record of your personal conversation with a mysterious and responsive cosmos, a conversation where every measurement is a question, and every outcome is an answer that forever changes the questions you ask next. Cubism places you at the center of a personal quantum narrative, but what happens when a narrative falls into a place from which nothing, not even information, is supposed to escape? This brings us to one of the most heated battles in modern physics, the black hole information paradox, a conflict that threatens the very logic of quantum timelines. At its heart lies a simple, devastating question. When something falls into a black hole, is its story erased from the universe forever? According to Einstein's general relativity, the answer is a grim yes. The gravitational pull is so intense that past the point of no return, the event horizon, not even light can escape. Every bit of matter that crosses that boundary, every atom, every particle, carries with it information, the specific arrangement that defined it, that told its history. Relativity says that information is gone, swallowed by the singularity, removed from our universe permanently. But quantum mechanics has a fundamental, unbreakable rule: information cannot be destroyed. It can be scrambled, hidden, or transformed, but it must be preserved in some form. If you could know the exact quantum state of every particle in the universe right now, in principle, you could run the clock backward and reconstruct everything that ever happened. The universe has a perfect memory, so here is the paradox. Throw a book into a black hole. The book burns up, its atoms are torn apart, but the quantum information that described its pages, its words, its story, must still exist somewhere according to quantum law. Yet relativity insists that information is trapped behind an event horizon, forever inaccessible to the outside universe. This is not just a technical disagreement. It is a fundamental clash about whether the past is permanent or erasable. If information can be truly lost, then the history of our cosmos is not a fixed record. It is a story with pages being burned as we speak, and the very concept of a consistent, traceable timeline crumbles. Physicists have proposed stunning solutions. One, deeply tied to the holographic principle, suggests the information is never actually lost. It is not that it falls through the event horizon. Instead, as an object approaches that boundary, its information is smeared and encoded onto the two-dimensional surface of the horizon itself, like a cosmic tattoo. The three-dimensional book is destroyed, but a perfect, scrambled holographic record of it remains painted on the black hole's skin. The information is preserved, but in a form so chaotic it is indistinguishable from random noise. Another solution comes from Stephen Hawking's own revision of his work. He originally showed that black holes are not completely black. They slowly leak energy, emitting a faint glow of what we now call Hawking radiation. This radiation, he first thought, was purely thermal, carrying no information about what fell in. It would be like the heat from a furnace, telling you nothing about what fuel was burned. But this led directly to the paradox, as the black hole would eventually evaporate completely, leaving behind only this featureless radiation and destroying the information forever. Hawking later changed his mind. He conceded that the radiation might not be random after all. Through incredibly subtle quantum correlations, the information about the infalling matter could be imprinted onto the escaping Hawking radiation, like a message hidden in static. As the black hole evaporates, it slowly and chaotically gives back the information it consumed, preserving the universe's quantum memory. The information is not lost, it is merely laundered through the most extreme physics imaginable. This leads to a breathtaking speculation about timelines. If a black hole does not destroy information but transforms it, what does it transform it into? Some theories suggest that the interior of a black hole is not a dead end but a gateway. The singularity might not be a point of infinite density, but a bridge to another region of spacetime. In this view, the information that falls in does not vanish. It becomes the seed for a new universe branching off from our own. The black hole in our cosmos is a white hole, spewing out matter and energy in another. Your timeline, if you were to fall into a suitably large black hole, might not end. It might simply continue elsewhere in a reality with its own laws and history, born from the quantum information of our own. A black hole, then, could be less a tomb and more a cosmic womb, a factory where the compressed information of one timeline becomes the Big Bang of another. This transforms these terrifying voids from endpoints into potential transformers of reality, where the story of one world becomes the prologue for the next in an endless fractal chain of creation. The black hole's paradox hints at information reborn, but could there be entire layers of reality built from particles we have never seen? This is the promise of supersymmetry, a beautiful, unproven theory that seeks to complete the standard model of particle physics. It proposes a profound symmetry at nature's heart, a partnership so deep that for every known particle in our universe, there exists a hidden twin. The electron would have a partner called the selectron. The quark would have the squark, the photon a photino. These hypothetical twins are collectively called superpartners or sparticles. They are not mere copies, however. They possess a crucial difference in a quantum property known as spin. This difference would relegate them to a shadow sector of reality, a parallel quantum plane that interacts with our familiar world only through the weakest of forces, primarily gravity. Imagine our universe as a bustling city visible in bright sunlight. Supersymmetry suggests there is an entire mirrored city occupying the exact same space, but made of a different transparent material, visible only in the faintest infrared glow. The citizens of these two cities, our particles and their sparticles, mostly pass through each other unseen. They live in the same locations in space-time, bound by the same gravitational field, but they are ghosts to one another, their interactions rare and subtle. This hidden sector could be far more than a particle physics curiosity. It might represent an entire hidden set of quantum timelines operating in lockstep with our own. In the many worlds interpretation, branches diverge based on the outcomes of quantum events involving our known particles. But what if every one of those branches has a silent counterpart? For every decision made in our luminous city, a corresponding shadow decision unfolds in the infrared city. The sparticle versions of you in this view are not making different choices. They are making the supersymmetric correlates of your choices, following a parallel but distinct set of quantum rules. Your timeline and your sparticle twin's timeline would be inextricably linked, two harmonies in a single cosmic chord, forever separated by the veil of spin. We would never directly witness their history, just as they would never witness ours, yet the gravitational footprint of their collective mass might be the very thing that holds our galaxies together, the mysterious dark matter we have been searching for all along. It is a universe of profound, unseen depth, where every story we live is echoed in a silent, shadow language of superpartners. The universe possesses a quiet but formidable immune system, a set of laws designed to protect the integrity of history itself. This is Stephen Hawking's chronology protection conjecture, a profound proposal that the cosmos will not tolerate the chaos of backward time travel. Hawking, ever the pragmatist, looked at the equations of general relativity and saw they permitted wormholes and closed time-like curves, theoretical pathways that could loop back to an earlier point in time. Yet he noted a glaring absence. We are not flooded with tourists from the future. Where are they? His answer was elegant and decisive. They are not here because they cannot be. The conjecture states that whenever conditions arise that could allow macroscopic time travel to the past, a physical process will always intervene to prevent it. The laws of physics, he suggested, contain a built-in self-defense mechanism against paradox. Think of it as a cosmic firewall for causality. One proposed mechanism involves quantum effects. Imagine you are trying to stabilize a wormhole, to hold open a tunnel through space-time long enough to send a person back to yesterday. As you pump energy into the system to keep the throat open, the very vacuum of space around it would react. According to quantum field theory, empty space is not truly empty. It seethes with virtual particles popping in and out of existence. A wormhole or other time machine geometry would focus this quantum energy, creating a feedback loop. The more you try to stabilize the time machine, the more intense this vacuum energy becomes. At the critical moment when the timeline might become a loop, this energy would skyrocket to infinity, overwhelming any possible structure and destroying the time machine before it could be used. It is not that the universe is malicious, it is that the mathematics of quantum fields and general relativity become violently unstable when forced to describe a paradox. Reality itself seems to crash, like a computer program encountering a fatal logical error. This conjecture acts as the ultimate guardian of our linear experience. It ensures that while particles might flirt with retrocausality on a microscopic scale, you and I, and all the macroscopic events that define our world, are forever locked into a forward-flowing narrative. The past is a protected country, its borders sealed by the relentless laws of physics. Your memories remain safe from revision by your future self, and history retains its singular, unchangeable weight. Hawking's idea offers a deep comfort. It suggests causality is not a fragile social construct, but a fundamental feature of the cosmos defended at the quantum level. The timeline we share is not just one possibility among many. It is a fortress, its integrity maintained by the universe's own relentless rules. This improbable perfection in our cosmic rulebook begs for an explanation. Why do the fundamental constants of nature align with such razor-sharp precision to allow for atoms, stars, planets, and ultimately, us? The strength of gravity, the charge of an electron, the energy in empty space. Tweak any of these numbers by even a fraction of a percent, and the universe becomes a sterile void. Stars would not ignite, or they would burn out in a flash. Complex chemistry would be impossible. This is the puzzle of fine-tuning, a cosmic coincidence so staggering it feels like a message. For many, it points toward a designer, a purposeful architect who set the dials just right. But within the framework of the multiverse, a different, humbling answer emerges, one that requires no designer at all. It is known as the anthropic principle, a simple but profound logical filter. It states that we can only observe a universe that is compatible with our existence as observers. We are not a random sample of all possible universes. We are a biased sample of one, the one that allowed us to be here to ask the question. Now, combine this with the infinite multiverse of eternal inflation, the frothing sea of bubble universes, each with its own random set of physical laws. In such an infinite ensemble, every possible combination of constants, every conceivable rulebook will be realized somewhere. The vast, overwhelming majority of these bubbles will be dead, sterile, or instantly collapsing. They will have gravity too strong, nuclear forces too weak, or dimensions that unravel. But in an infinite froth, even the most improbable outcome is not just possible, it is guaranteed to occur an infinite number of times. Our universe is not a miracle, it is a statistical inevitability. We do not live in a special cosmos fine-tuned for life. We live in one of the habitable ones, a rare but absolutely necessary oasis in a desert of cosmic dead ends. There is no deeper purpose or guiding hand required, just the cold, relentless math of infinity playing out across an endless landscape. This perspective transforms our place in the cosmos. We are not the intended product of a grand design. We are a fortunate accident, a lottery winner in a game with an infinite number of tickets, where the prize is simply the ability to look around and wonder why you won. The fine-tuning we perceive is not evidence of a plan, but a consequence of our own existence, a selection effect written into the logic of reality itself. It means the constants of nature are not messages, they are simply the local bylaws of our particular cosmic neighborhood, one lucky draw in an endless cosmic lottery where most tickets are blanks. The threads of quantum connection may not be limited to the space between us, but to the gulf between now and then. Recent experiments have achieved something that sounds like pure fantasy. They have entangled particles that never existed at the same moment. This is temporal entanglement, a phenomenon that ties the quantum state of a particle in the present to the state of a particle that existed or will exist in a different time. In one landmark experiment, scientists created a pair of entangled photons. They measured one photon immediately, determining its polarization, but they delayed the measurement of its twin, storing its quantum state in a crystal for a tiny fraction of a second before reading it out. Astonishingly, the measurement of the second photon made later was perfectly correlated with the measurement of the first made earlier. They were entangled across time. The particle measured in the future knew the state of its partner from the past, even though that partner was long gone. This is not a memory trick. It is a fundamental linkage that treats time as just another dimension through which quantum information can be non-locally connected. To grasp the strangeness, imagine writing a letter to your future self, sealing it in a box with a quantum lock. You then destroy the key. Years later, your future self opens the box. The moment the lock is touched, the act of opening it determines what the message inside says, and that determination instantly rewrites the content of the letter you wrote years in the past. The past and the future are not separate chapters, they are co-authors, writing each other into existence through a quantum dialogue. This suggests our linear model of time, where the past is fixed and the future is open, is a classical illusion. At the quantum level, the distinction between past, present, and future may be as fluid as the distinction between here and there. The timeline is not a river flowing in one direction. It is more like a woven tapestry, where threads from what we call yesterday and tomorrow are knotted together into a single, inseparable whole. If particles can share a state across time, then events might not be isolated points on a line. They could be nodes in a network where influence and information can flow along connections that defy our everyday sequence. Your present moment might be subtly shaped by quantum whispers from futures that have not yet fully formed, just as your past actions might be sending ripples into possibilities yet to come. The solid ground of cause and effect begins to feel like shifting sand, revealing a cosmos where all moments are quantum neighbors, eternally linked in a dance that transcends when they happen. The quest for a final theory is the search for a single, elegant equation that could fit on a T-shirt, yet describe everything from the birth of a universe to the flicker of a thought. This is the dream of a theory of everything, a framework that would finally unite the two great pillars of modern physics, the bizarre, probabilistic world of quantum mechanics and the smooth, geometric curvature of Einstein's general relativity. For over a century, these two theories have described reality with stunning accuracy, but they speak fundamentally different languages. One governs the impossibly small, the other the immensely large, and where they meet at the edge of a black hole or the first moment of the Big Bang, our understanding breaks down into nonsense. A theory of everything would be the universal translator, revealing the deeper grammar from which both sets of laws arise. Leading candidates like string theory and loop quantum gravity offer wildly different visions of this foundational layer. String theory proposes that at the heart of all matter and forces are not points, but unimaginably tiny, vibrating loops of energy. The different vibrations of these strings give rise to different particles, much like different vibrations of a violin string create different notes. In this symphony of strings, gravity, electromagnetism, and all other forces emerge from the same harmonic principles. Loop quantum gravity, in contrast, suggests that space itself is woven from a network of finite loops, a dynamic fabric where geometry is quantized. Here, gravity is not a force transmitted by a particle, but the natural curvature of this quantum tapestry. So how might a successful theory of everything finally illuminate the mystery of quantum timelines? The answer lies in how it would describe the fabric of reality at the absolute foundation. In string theory, every particle, every event is a vibration. A quantum timeline, then, might not be a branching path through a landscape, but a resonant pattern within a higher dimensional reality. Each possible history could be a different vibrational mode of the cosmic string, a different chord struck in the multiverse. The act of observation, of measurement, might be the process that selects which vibration we are tuned into, which frequency our consciousness decodes into a solid sequence of events. The other timelines would not vanish. They would simply be other harmonies in the symphony, playing simultaneously but unheard by our local instruments. In loop quantum gravity, where space-time is a network of relationships, a timeline could be understood as a specific weaving through the spin foam. Each possible event is a knot or intersection in this eternal network. Our lived experience of time would be one coherent path untangling itself from the knot, a story told by following one consistent thread of cause and effect through the frozen sculpture of all possibilities. A theory of everything would tell us why that particular thread feels continuous and real, while countless others remain as potential patterns in the quantum weave. Ultimately, such a theory would not just catalog the ingredients of reality, it would explain why reality has the structure it does. It could reveal whether multiple histories are a necessary mathematical consequence of a unified cosmos or an illusion born from our limited perspective. It might show us that timelines are not separate, parallel worlds, but interdependent vibrations of a single, unimaginably complex entity. The search for this final theory is more than a technical puzzle. It is a journey to understand the stage upon which all possible stories, including our own, are performed. Finding it would be the moment we stop reading the universe's script and finally understand the language in which it is written. From the branching paths of many worlds to the silent code of the holographic universe, this journey has spanned 30 breathtaking visions of reality. We have seen timelines split, merge, and loop back on themselves, witnessed universes born from collisions in higher dimensions, and considered the possibility that our own consciousness is the thread weaving through the quantum tapestry. Each theory, from the elegant determinism of pilot waves to the cosmic censorship of chronology protection, represents a profound attempt by the human mind to answer the oldest questions: where did we come from, and what is the true nature of the stage upon which our lives unfold? While many of these ideas remain speculative, existing at the very frontier of physics and philosophy, they are not mere science fiction. They are the rigorous, often beautiful, extensions of our best mathematics and our boldest thoughts, the cutting edge of human curiosity pushing against the limits of the knowable. They remind us that reality is far stranger and more wondrous than our everyday experience suggests. So as we stand at the edge of this vast landscape of possibilities, we leave you with one final, deeply personal question. Which of these theories feels most real to you, and what does that choice reveal about the nature of your own reality? The answer is yours alone. If this exploration has shifted your perspective, let us know in the comments below, share your thoughts, and join the discussion. For more journeys to the edges of understanding, be sure to like this video and subscribe. The mystery continues.